Hello students, welcome to Chem Expert classes. I hope you all are doing amazing. I have brought another session for all of you on the arrangement of electrons in the transition element. Before this video, I have discussed in the previous video the basics of this, right? Which is quantum numbers, what are quantum numbers, what are shells, what are orbitals, what are subshells, all of these things we have already discussed in our previous video. So if you haven't watched the previous video, I will highly recommend you to go watch that video first and then come to this session, right? So in this one, we are going to discuss the transition elements in detail, right? The first and the foremost thing which you should know is the off-burst principle. Off-burst principle. Now, according to off-burst principle, the electrons are filled in the atom in accordance to the increasing energy of their orbitals, right? When we are filling the electrons inside the orbitals, then we look at the energy levels or energies of those particular orbitals in which we are filling the electrons, right? So ऑफबर्न ने ये बोला था बेसिकली कि जिस ऑर्बिटल की एनर्जी कम होती है उसमें इलेक्ट्रॉन पहले फिल होते हैं एंड देन उस ऑर्बिटल में जिसकी एनर्जी पहले वाले से थोड़ी ज्यादा है एंड देन द नेक्स्ट वन हैविंग लिटिल मोर एनर्जी एंड देन द नेक्स्ट वन and so on and so forth. So according to off-burst principle, the electrons will be filled in the orbitals in accordance to the energies of the orbitals, right? Now how will we know किस orbital की कितनी energy है, और particularly if we say किस orbital की energy कम है और किस orbital की energy ज़्यादा है, वो हमें कैसे पता चलेगा? So there is one rule for that which is called N plus L rule. N plus L rule, okay? Now N over here is the principal quantum number, whereas L is the azimuthal quantum number. I will again tell you, if you haven't watched my previous video, please go and do that and then come back to this video, right? That is very important for you. All right, so N plus L rule says that this is principal quantum number and this is azimuthal quantum number. Now if we say, for example, for the orbital 1s, right, here the value of N will be 1, right? 1s value of N is 1. For S, the value of L for S is always 0, right? So for S, the value of L is 0. Now if we do N plus L, the value is going to be 1 plus 0, that is equal to 1, right? So the value of N plus L is equals to 1. That means N first electron will go into this orbital, 1s orbital. Now coming to 2s, so the value of N is 2 over here, value of L is again 0 over here. So what will happen? 2 plus 0 is equals to 2. Now you can see over here is that the value of N plus L is equal to 2 for 2s and 1 for 1s. That means the electron will be filled in the orbital which has the lower number of the N plus L value. So which one of these has lower number? 1s. So electron will be filled in 1s orbital first and then in the 2s orbital. Now we will do for 2p orbital. So for 2p orbital, the value of N is 2 and the value of L is 1. So the value will be 2 plus 1 is equals to 3. Here you can see the value over here is 3. That means first our electrons will be filled in the 1s orbital, then 2s and then 2p. Now looking at after 2p, we have of course 3s. So the value will be 3. For s it is 0, value of L. That means 3 plus 0 is equals to 3. The value is 3 here as well as here. Now in this case, if the values are same, then we go for the lower value of N. So for 2p, the value of N is 2 and for 3p, the value of N is 3. So we will go with this one, 2, okay? That means the electron will be filled, if the value of N plus L is same, then the electrons will be filled in that orbital in which the value of N is the lowest, okay? So this one will be filled first as in before 3s. Okay, so the electrons will go first in 1s, then in 2s, then in 2p and then in 3s. Now for 3p we will do 3p. The value is 3 plus 1, that is going to be 3 plus 1 is equals to 4. Here we can see the value is 4. So after 3s we will fill 3p. Here you can see for 3d the value is going to be for N 3, and for D, L value is going to be 2, right? For D, L is equals to 2. So it is going to be N plus L is 3 plus 2 is equals to 5. Here you can see the value of N plus L for 3D is 5, right? So 3D will be filled after 3P, of course. Now we will do the same thing for 4S. Here, look at this very carefully. The value of N is 4 and the value of S is 0. So the value comes out to be 4 plus 0 is equals to 4. Now look at this very carefully, okay? The value of the N plus L is 4 for 4S, which is in the next shell. Value of N plus L for 3D is 5, which is in the third shell, right? So that means after filling 3P, the electron will not go to 3D, because according to Aufbauer's principle, the electron will be filled in accordance to the value of N plus L. The orbital having the lower value of N plus L will be filled first. So here you see 3P has value 4 and 4S also has value 4. So here value of N is equals to 3. That means the value of N is lower as compared to value of N over here, which is 4. So the electron will be filled in 3P, but after 3P, the electron will go to 4S and not 3D. This thing you have to keep in mind. This is very important. Now I hope this is clear to all of you. Now we will begin with the atoms having lower atomic numbers, and then we will slowly move towards the transition elements, right? For example, हम hydrogen example ले लेते हैं. So hydrogen has atomic number of 1. So what will be the electronic configuration, right? So suppose now for hydrogen we have 1s orbital first. So there's only one electron. So one electron will go in 1s orbital like this. So the electronic configuration will be 1s1 for hydrogen, correct? Now talking about helium, the atomic number is 2. So electrons will go in 1s orbital, of course. So one electron in this, and of course you know that one orbital can accommodate 2 electrons, so the second electron will also go in this one only. But look at this very carefully. I have drawn one orbital in the upward, one electron in the upward direction and the other one in the lower direction. This indicates that no 2 electrons in the same orbital can have same spin, right? Same spin नहीं हो सकता है बच्चे. One is going to be up spin and one is going to be down spin. That means if one is rotating in the clockwise manner, the other one will be rotating in the anti-clockwise manner. I hope this is clear to you. This is also known as Pauli's exclusion principle. Pauli's exclusion principle. So this also you have to keep in mind, that no 2 electrons in the orbital can have all the same values of all the quantum numbers. That means here if you see, both these electrons have the same value of N, of course, same value of L and the same value of ML as well, because they are present in the same shell, same subshell and same orbitals. But are they present? Are they having the same spin quantum number? No. One is having plus half spin and the other one is having minus half spin. So while doing or writing the electronic configuration, you have to keep in mind this as well. This is called as Pauli's exclusion principle. One electron is going to be up spin and one will be down spin always, right? Okay, so I hope this is also clear to you. Now talking about the third one, which is lithium, having atomic number 3, right? So 1s, okay, and then we will need the second shell as well. So second shell has 2s, then has 2p, correct? Now first electron will go in 1s, of course. I hope this is clear. 1, and then now it is filled. Now the second one will also go in this one, because first shell can accommodate up to 2, one orbital can accommodate up to 2, right? And now the third one will go here in 2s. So we can say the configuration is 1s2 and 2s1. I hope this is clear to all of you. So here I have written a few elements for all of you, and we are going to fill the electrons in these orbitals, right? So we will start with beryllium, having atomic number 4. Okay, so beryllium has 4. So 1s, first electron will go in 1s, second will also go in 1s. Okay, now comes 2s, 1 and 2, right? So 4 electrons are completed. So 1s1, 1s2, 2s2, 1s2, 2s2 for beryllium. Now coming to boron, 1 electron goes in 1s, 2, 3, 4. 4 are complete. Now the next one will go in 2p. Correct? The next one will go in 2p. Understood? So configuration will be 1s2, 2s2 and 2p1 for boron. Now coming to oxygen. Look at this very, very carefully. So 1s1 and 2, 1 and 2, 4. Now 4 are left. So 1, 2, 3 and then 4. Look at this very, very carefully. What I am trying to tell you over here is, now in 2p, suppose, can we write it like this? 1, 2, 3, 4. Can we write it like this? No, we cannot. This is wrong. Why? This is because of Hund's rule of maximum multiplicity. Now, Hund's rule of maximum multiplicity says that the pairing of electron in the orbitals, the degenerate orbitals, that means the orbitals of the same subshells, cannot take place until each electron is filled, singly filled, or each orbital is singly filled. That means जब तक 2px, 2py and 2pz तीनों singly filled नहीं हो जाते, तब तक the fourth electron cannot start pairing. ऐसा नहीं हो सकता है that these two start pairing in the first one and the second one the 2 electrons are present and the third one is empty. No, that cannot happen because of the fact that these have the same energy. So electron will be distributed in all 3 first and then only pairing will start. So this is known as Hund's rule. Hund's rule of maximum multiplicity. I hope this is also clear to all of you. Clear? So we have discussed of Bauer's principle, then Pauli's exclusion principle, and then Hund's rule. While writing the electronic configuration of any of the elements, you have to keep in mind all these 3 rules. Okay? Now coming to fluorine, of course, 1 electron, 2, 3, 4, 5, 6, 7, 8, and 9. Clear, everybody? Okay, for neon we'll do 1s2, 2s2, 3, 4, 5, 6, 7, 8. Right? So 10 electrons are filled in this one as well. Right? Now 2s is also filled, 2p is also filled. Now the electron will start going to the third subshell, that is 3s, 3p. Now we will do the electronic configuration of these 4 elements. Okay, starting from sodium, we have 11 electrons. So 2 electrons will go in 1s, 2 in 2s, 4, 5, 6, 7, 8, 9, 10. 2p is completely filled, second shell is completely filled. Now the next electron will go in 3s shell, right, orbital. Right? So it is going to be like this. For argon we will do, okay, I want you to do for all the elements between these, right? Okay, I will not do all, you will have to complete. Now for argon, if you do, we have 18 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. You can see I am doing the pairing only after completing the orbitals singly, right? Only after filling it singly. Then only I am doing the overlapping or basically pairing, correct? Then only I am doing the pairing. Clear? So this is done till argon. For potassium, we have 19 electrons. Now you know that the electronic configuration we generally write for potassium is KLM. So 2, 8, 8 and N 1. Correct? This is what we write for potassium. We know that the first shell, that is the second shell, that is the K shell, can accommodate maximum of 2 electrons, L can accommodate maximum of 8 electrons, but M can accommodate maximum of 18 electrons. Even though it can accommodate up to 18 electrons, we do not fill the 9th electron in here. Why? Now I will tell you the reason why. So the reason over there is, of course, N plus L rule. We know that the energy of the 4s orbital is lower as compared to the 3d orbital, which is present in the third shell, right? Therefore, the electron will go to the 4s and then to the 3d. Now, once the 4s is completely filled, then only the electron will start coming back to the third shell, that is in the 3d orbital. I hope this is clear to you. I will explain this with the help of the diagram. In potassium, we have the first shell, second shell, the third shell, and the fourth shell. All right. Now, the electrons, 2 electrons can be accommodated here. Then 1, 2, 3, 4, 5, 6, 7, 8. 8 here. Then 1, 2, 3, 4, 5, 6, 7, 8. Now this completes 18 electron, that is argon, right? Now 1 electron must go to the third shell only. Why? Because we are still left with 3d orbital. The third shell has 3 subshells, 3s, 3p and 3d. 3d is still left, but we do not accommodate electrons here because of the off-pass principle, saying that the 4s has lower energy as compared to 3d. So electron will move here in the fourth shell. Understood? Okay. So if we write the electronic configuration over here, so it will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. I hope this is clear. So for calcium also 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 and 20. Okay, so that is why the configuration of calcium is KLMN2882 and not KLM2810. This is wrong. Why? Because the electron will start going to the fourth shell once 3p is completely filled, in accordance with the off-pass principle. Now, these are not transition elements. We have not started with transition elements yet, right? So, these are the elements starting from atomic number 1 to atomic number 20. I hope this is clear to you. Now, we will quickly move to the transition elements. So, now starting with transition elements. Okay. So, for transition element, starting with scandium, having atomic number 21. Alright, 21. So, look over here this is the 1s orbital, then the 2s orbital. So, 2 electrons in the 1s orbital, 2 in the 2s orbital, then the 2p orbital, 1, 2, 3, 4, 5, 6. Total 10 orbitals are completed. 1s, 2s and 2p. Now the 3s orbital according to the energy, 3s. So 1, 2. Now 12 electrons. Now 3p orbital, 1, 2, 3. 1, 2, 3, 4, 5, 6. 18 electrons in total. Now the electron will go in the fourth shell, the 4s orbital. So 4s. Now the electrons, how many are left? These are 10 and then 8. 18 electrons, we are left with 3. So 4s will have 2 and then the electron will go in 3d. So 3d orbital. Then the electron will go to the 3d orbital. I hope this is clear to all of you. We can write the configuration as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1 for scandium. This is the electronic configuration of the first transition element, that is scandium. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d1. I hope this is clear to all of you. Now moving to the next one, scandium ke baad we have vanadium 22. So it is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now we are left with 2. So 2 will go in 3d2 of course, right? So the second electron for scandium, if I write here, sorry, for vanadium, the second electron will also come here in 3d. I hope this is clear to you. Okay, now coming to the third one, which is going to be of course titanium 23. If we write titanium over here, so it is going to be again same 18 electrons will be filled just like this, 20 electrons will be filled just like this, and the next one will come in this 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d3. So for titanium it is going to be 3d3. Clear everybody? So if we start with chromium, which is having atomic number of 24, then again 18 electrons will be filled here, 1s2, 2s2, 2p6, 3s2, 3p6 and then 4s2. So for 24 it can be 3d4, right? So the configuration should be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d4, right? This is going to be the configuration, but no, this is absolutely wrong. This is not going to be the configuration for chromium. This is an exception. Okay, listen to me very, very carefully. What happens in this case over here is, now if we look at the 3d orbital, right, it is having 4 electrons in it, right? Now this electron, instead of going in the 4s subshell, in the 4s orbital, will go to the 3d orbital. Why? Because when the 3d orbital is having 5 electrons, then it is half-filled configuration, half-filled orbital, and the half-filled orbital or the fully filled orbitals are very, very stable, right? So what happens over here is, if we look at 3d, 1, 2, 3, 4, right? 3d, so electron 1, 2, 3, 4, 5. Now this is half-filled orbitals. After this pairing will start taking place, correct? So this is 3d5. Now because of the fact that there is symmetry, now because the 3d orbital is symmetrical, now all are filled, half filled. Now due to the symmetry, the 3d orbital is very, very stable now, correct? Understood? I hope this is clear. So the electron, instead of going to the 4s subshell, will go to the 3d. Why? Because that is going to be more stable. Also, when there is a half-filled configuration, then electrons can exchange their positions, right? This electron can go here, 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 anywhere, and these can also exchange, right, their positions. Now this energy, they release energy when they exchange their position, and this energy is known as exchange energy. Due to this energy as well, there is always stability. Alright, so more the exchange energy, more is the stability. So due to two factors, that is symmetry first of all, and second one is the exchange energy. 3d5 half-filled d orbital, or any orbital half-filled for that matter, is obviously more stable. So instead of this, the configuration of chromium is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5, or we can write 3d5, 4s1. I hope this is clear to all of you. This is an exception because of more stable singly half-filled 3d orbital in this case. Clear? Now talking about the next element, which is manganese, having atomic number 25. Now 25, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d5. Correct? So this is going to be the same, and then manganese 25, we are going to have last electron in 3d5, 4s2. For chromium, it was 3d5, 4s1. Now for this manganese, it is 3d5, 4s2. Now this is also half filled, correct? But the second electron will go in 4s. I hope this is clear to all of you. Now coming to iron, 26. Again, same thing, 4s2. Now the pairing will start happening according to Pauli's exclusion principle. Electron will go in this. So it is going to be 3d6, 4s2. I hope this is clear. So manganese, iron, now cobalt, 27. 3d7, 4s2. Clear everybody? Okay, please do this configuration in your notebook so that it becomes clear to you. If you have any doubt, Please put it in the comment section. For cobalt, it is 27. I want you to write the entire configuration and show it to me. Put it in the comment section, okay? Write it or put the image in the comment section. We will definitely discuss everything in the comment section, okay? Do this configuration, write the entire thing like this and then the entire configuration and show it to me in the comment section. So now we are doing for nickel. Nickel is 28, of course. So 28, now this is going to be 28. So this becomes nickel 28 is going to look like 3d8 4s2. I hope this is clear to everybody, right? Now after nickel, the next one is copper. Now for copper, the atomic number is 29. Now look at this very, very carefully. For 29, if we do copper 29, for 29, again the same thing will happen over here. If we put one electron here, correct? Now, this electron will also come here. Why? Now, because we cannot write it as 4s2 and 3d9. Instead of that, we will write it as 3d10 and 4s1. Why? Because 3d10 is a completely filled orbital, and half filled and completely filled orbitals are more stable, as I have already told you. Now, because of symmetry and because of the exchange energy, of course. So for copper, it is also an exception. You have to keep in mind, chromium and copper 4s2 nahi hota hai. It is 4s1, 3d5 for chromium and 3d10 for copper. I hope this is clear to all of you. Write the configuration, put it in the comment section, everybody. Alright? Okay, so we are done with copper. Now, after manganese, iron, cobalt, nickel, copper, we have zinc. Now, zinc is 30, last one. Okay, so 31, what will happen? The electron will go to the 4s. Now, this is going to be 3d10 4s2. I hope this is clear to everybody. Okay, zinc will have 3d10 4s2. Correct? Now, the transition elements are done. Till here, till zinc, we are done. Okay, now I hope you have understood the entire session. I hope you will do all these in your notebooks, right? So that it becomes clear to you. You have to practice. You have to also keep in mind all the principles and the exceptions, chromium and copper. Why also you have to remember. Okay, if you have any doubts, you've not understood anything or any topic which you want me to pick and make a video on, you can put everything in the comment section. I will definitely make a video for all of you on that. See you in the next one. Take care. Bye-bye.